So yeah, I'm going to talk about dependently typed state machines in a language called Idris. So hopefully this is interesting. I apologise that it may not be as useful in production, and you probably can't take it home to use in your day-to-day job right now. But it's interesting, and it's something that we should probably be looking at. So yeah, my name's Tim McGilchrist. I currently program Haskell and a lot of OCaml at the moment at Ansarada. I'm doing machine learning, feature extraction, natural language processing, that sort of thing. My academic interests, I suppose, are in distributed systems, so implementing consensus algorithms, that sort of thing. And I'm convinced about types. I've been doing Haskell for 5 years, sort of seriously as a work thing. And every time I go back to looking at Python or Ruby or JavaScript, I'm horrified and very uncomfortable. So I kind of need types. It's like my coping mechanism now. Code review without types just doesn't work for me. So some backgrounds about problems. This guy looks like he's got problems. He's standing on the edge of a bridge. There's two people there, actually. So we've got to think about the sort of problems that we might have day to day and that might motivate us to look for new tools. And so what I realised in my day-to-day work was that I was seeing a lot of state machines embedded in just about everything, state machines embedded in your network stack. So this is a really terrible PostScript to PDF to image capture of a TCP/IP state machine, but you can kind of make out that there's some entry into the state machine at the top, and then you go through and there's various states, which are these boxes, and there's various transitions between them. And for something like TCP/IP, it's reasonably complex. Like there's a lot of arrows, there's a lot of conditions on those arrows, there's lots of states, there's moving between those things. If you think about how you might go about implementing that, there's obviously lots of logic, and there's lots of conditionals or preconditions or postconditions on each one of those movements between states. So you start thinking about that. There's lots of things to check. There's lots of code you have to write, possibly lots of errors in there. Another one that's close to my heart is talking about a consensus algorithm called RAFT. And this is just part of the RAFT algorithm. So this is the state machine for how they elect a leader in RAFT. So we start here we go into startup mode. So all of the nodes start up and they drop into a follower state. And then after some time, there's a timeout. They go to a candidate state. Some voting happens. And then at some point, someone gets elected to be a leader. But there's only 3 states, but there's a whole bunch of different transformations between those states, and there's preconditions, there's postconditions that you have to keep in check. So it's even for 3 states, it's reasonably complex. And if you start thinking about how am I going to get all this right, am I going to remember to check the preconditions, postconditions on everything? Am I going to get a bug? Am I going to get a leak in something? Even more importantly, I suppose, if you're thinking about security algorithms and that sort of thing, you're going to implement it incorrectly and you won't know until someone owns your system and takes all your money or leaks all your data to somewhere. So these state machines are coming up everywhere. So what I want to do as someone that's convinced about types is I want to use types for everything. So I initially I turned to Haskell, but the story for dependent typing in Haskell is still evolving at the moment. So as a better Haskell or a better implementation of the types that I want to use in Haskell, I turn to Idris, which is as the language creator. So Edwin Brady is the language creator for Idris. As he said, it's a Pac-Man complete language. Although I haven't seen a Pac-Man implementation in Idris yet. So if someone could write that, that'd be really good. And I could stop making that joke. But the idea behind Idris is that it's a general purpose language, unlike some of the other dependently typed languages like Coq or Agda or something like that, which are about proving programs. Idris is more concerned with actually implementing things, and then the proof part of it is sort of secondary concern, or is not as much of a focus of the language. So, yeah, we've said dependently typed language. So the start of the paper that introduced Idris to the world, written by Edwin, was this question of, which I put down the bottom, is what if Haskell had fully dependent types? And that's a really powerful thing to think about. So what are dependent types? Dependent types are types where values can appear in place of where other types are, and we'll get to some code later. But it's a similar shift from going from an untyped language to a typed language, and then you go to a dependently typed language. It's more complex, but you can express a lot more things in it. So we've got full dependent types, we've got dependent pattern matching, it's got eager evaluation, so unlike, say, Haskell, which is lazy, this is strict, so it'll evaluate the arguments to a function before calling the function. And it's got something equivalent to Haskell's type classes, but they call them interfaces, and your implementations are called implementations. So it's kind of similar. And I apologise if people don't know Haskell or PureScript or maybe OCaml. Some of the types might be hard to understand, perhaps, but we'll hopefully be able to explain what they mean. So yeah, my problem with state machines, and usually people's problems that they're trying to solve with dependently typed languages is to do with the length of vectors and how long they are and making sure you add them together properly. But I've got other problems. So I didn't want to choose that problem. So yeah, this is the classic dependently typed language joke. So this is the documentation for vector, and it says that you can add vectors, and vectors encode the length of the vector in there. And if you go to it like a academic FP conference, this is like on the bingo card. This is like at least one of the squares on the bingo card. But you get to see the nice doc for vector there. So in thinking about the state machines problem, which was probably about 3 years ago, someone linked a paper called States All the Way Down, again by Edwin Brady. And looking through the paper, I was reading the abstract and thought, wow, this is sort of ticking off all the things that I want to do with dependent types, and I want to think about for building things with state machines. So he talks about a useful pattern independently typing is to define a state transition diagram or a state transition system. It gives an architecture for how to build applications with state machines. So not just a single state machine, but how to compose state machines together and build something useful, and how to combine them into a larger system, which existing encodings of state machines that I'd seen didn't really talk about or didn't address as well. So these are sort of my requirements for some useful encoding of state programs. So the types should capture the states of the resources that I'm thinking about, and I shouldn't have to. It should be concisely capture those states, so I shouldn't have to encode things that I don't want to care about. The stateful APIs should compose, so if I've got one stateful thing and I've got a second stateful thing, I should be able to combine those together, and I should be able to implement something on top of those two, which is also stateful using those. The types should be readable. If you've done any dependently typing programming in Coq, Agda, Haskell, the types are never readable. And the error messages in particular are horrific, I think it's safe to say. They're getting better, but you need to understand how they're encoded in the language, plus the dependent typing to actually decode what it means. So let's get on to the recipe. So the recipe outlined in the paper was this. So first you draw your state diagram for the problem. Drawing state diagrams is why everyone should have a whiteboard in their office. It's like mandatory, it's like a keyboard, you must have it. Then you define your state machine as a type. You implement some state machine functions on top of that state machine type, and then you define a way of running your state functions. So we're going to go through each one of those, and we'll look at some code for them. So this is my state machine. It's only got 2 states because I'm no good at drawing diagrams, and it's simpler. This is also evidence of why I'm not a graphical designer. So we've got 2 states. We've got a logged in state and a logged out state. And we've got some arrows, so we can log in, and if it's successful, we go to the logged in state. If we log out, we go back from the logged in state to logged out state. If we log in and it's a failure, we stay in the logged out state. And if we're logged in, we can access some sort of protected secret resource. So fairly simple. And this is our encoding of that particular diagram. So you can see at the top there, we're importing a couple of packages. This state paper introduced a module called control.st. So that includes a lot of the machinery for encoding these. So we can see we've modeled our access, so log in, log out. We've got some sort of data type for the result of whether we've logged in successfully or not. So we've got an OK or a bad password. They should be fairly familiar to people, hopefully. And then we've got this interface, which, as we said, is a type class, or equivalent to a type class in Haskell or Scala. So we've got store is our resource that we're dealing with. And we've got a bunch of functions on here. So we've got a connect, so we can connect to our store. We've got a disconnect to our store, and read some sort of secret. So the interesting thing with these, can I get a mouse? No. Okay, so the interesting thing with these is that there is dependently typed functions all through this. And it's really they're kind of hiding because it looks like type signatures. So let's decode this ST. So this is our state type that we're getting from control state. And so we can read this as state, and this M is some sort of underlying monad. This is the return type from the function, and these are the resources that it uses. So if we look at the connect one, it's taking in some sort of variable, and then it's adding a store state of logged out. So it's initializing the resource. So we can't create it out of thin air. We're sort of initializing it with something. And the disconnect, we can see, takes the store, which is what our var is, and it's also in a monad. It returns nothing, but it removes this store logged out from our list of resources. And similarly for read secret, we've got, again, we're taking some sort of string, it's returning some sort of string, which is our secret value, and it's ensuring that we are in the logged in state. So we can't call this unless we're in the logged in state. And then the last couple of functions that we want is we want some way of logging in and some way of logging out. And these ones are a little bit more hairy because I can't reach for there. So again, we've got this ST, and we've got an M, which is our monad, and we've got some sort of login result, which is the return type, and we've got a precondition of we need some sort of logged out store. And then we've got this weird sort of colon arrow function-y type thing with, it's like res and store and that. So that's our type level function. So that's basically saying that we're going from the logged out state to the logged in state, but we don't always log in successfully. We've got 2 options there. We can either provide the correct password or we can provide the incorrect password. And depending on which one we provide, we can get a return type of either logged in or logged out. And so we're handling that logic at the type level rather than at the function level. So it's enforcing the fact that we need to consider those 2 cases. We can't ignore one. The compiler won't let us compile the program if we don't do that. And log out is maybe less interesting. It's just taking a store that's logged in and it's going to a logged out state. So it's saying if you want to log out, you have to already be logged in, and then you go to the logged out state. What are the type level functions? The other interesting type level function here is the triple colon, which is you can think of it as a way of accessing labeled values within a list. So these resources we're talking about are a list of a label and the resource. And so there we've given store is the label, and we're just accessing that. Does that sort of make sense, hopefully? So that's our type. So our type is this. This is encoding our state machine, and this. So that's our equivalent type class. So let's use it for something. So we want to get the data. We want to get our secret data. We've got a couple of type classes there of console IO, so you can think of that as monad IO. And we've got some sort of data store M, which is our type class that we had before. And then our type here is ST of a monad and goes from an empty list to an empty list. So it starts with no resources and ends with no resources. So it ensures that we clean up after ourselves. And so we go through each of the steps, we connect, and you can see at the login stage, we have to handle the bad password. So we're pattern matching on OK, but we also have to handle the bad password. So we could do that with a case statement, but there's some special syntax, which is that pipe operator that is handling the bad password state. And you'll notice with the bad password, we're printing out something, but we also forced to call disconnect to clean up our resources. So the types are forcing us to implement or to use this in the correct way. You could imagine if this was rather than a data store, it was some database connection, and you went to connect and then you got an error and you went, oh yeah, I'll just print it out and I'm done with it, and you delete connections. This is forcing us to do the right thing. And then looking at the success case, we're reading the secret and we're printing it out, and then we are forced to go log out, disconnect. So the types are guiding us to implement it correctly. It's not just modeling the data correctly. We have to implement the function correctly. And so I included this error, which is kind of intimidating, I suppose. But it's reasonably formatted, and what it's laying out is the preconditions and postconditions for calling particular functions in there. So it's the preconditions. So this was when I deleted the login part and didn't handle that properly. So it gave me the preconditions of preconditions of logged in, and then the states where I had to handle both cases. The postconditions were that I had to be logged in, and the resulting states. So it's kind of guiding me. It's telling me, similar to type holes in Haskell, it's guiding me of what states I need to handle. So it's hard to do it incorrectly. The types guide you. So that's using it as a consumer via the type class. And this is a implementation of the data store in the IO monad. So we're initializing our store as a state monad with secret or string. So it's got a string data type in there. We could store something else in there if we wanted to. And then we're just going through and implementing each of those functions that we had on our type class. There's the new delete and read functions work on what you can think of as a mutable variable, I suppose. Some sort of stateful variable that you've created, like an mvar or something from Haskell. And so that you're creating a new one and you're putting the secret details in there and returning it back into the monad. And delete read are fairly straightforward. And then login is going through and pulling that value out, checking it against friend, and then returning OK or bad password. And then you just run it like you would a regular sort of either or something monad transformer. So we're just running it and this will bring in the I/O properly, and it'll give us the interaction, and we'll be able to read from console and that sort of thing, and enter the password, and that is all good. And if that compiles, we've followed our types and we've implemented it correctly, and we can't do the wrong thing. So I think that's really cool. If you do something similar with free monads or other implementation techniques, you can implement it incorrectly and not know that you've done it. So there's a couple of different types of composition that I wanted to cover. There's the idea of horizontal composition, so multiple state machines within a function, and vertical composition, which is implementing state machines in terms of other state machines. I'm only going to do horizontal because I don't have enough time to do vertical, and it's a little bit more complicated. But you can think of examples of where you might want to implement a state machine on top of a state machine. So this is taking our data store or get data function and adding fail count. So we're going to count the number of failures that we got when we logged in. And you can see that we've got a fail count variable there that's coming in, and we've added fail count as a state integer monad up the top here to our list of types. And so I've put this call function in everywhere to show where we're sort of getting a subset of those resources. So connect only takes the data store. It doesn't take the fail count. So call lets us get a subset of the resources and just pass the ones we need into the correct functions. You can get rid of call with using, there's a implicit that you can use that will get rid of the call, and it'll line up the types and the functions depending on what data they take. And this is the somewhat complicated function here, but this is basically just saying it takes a subset of the resources that function needs, applies the function, and then rebuilds the resources afterwards. But if you rewrite that with the implicit calls, it will get rid of all of that. So that's one way of combining two different states together. Yeah, I don't think we've really got time to go over this particular one, but this is really cool, implementing states on top of implementing a higher level state in terms of other lower level states. And the basic idea is that you use these composite resources, which is the data type here, and functions called split and combine, which let you peel off a particular resource, implement your functionality in terms of that, and then recombine them. So it's a similar sort of approach to what we were doing with the call, where we were subsetting the resources and only using particular ones. So that's kind of like the final cleaned up version of the data store. So I think it reads really nicely personally, but it might not for everyone. But you can kind of clearly see in the types what states are preconditions, what states are postconditions, what is being returned from a particular function. And it's quite readable, and you could imagine almost even generating documentation and generating your state machine diagram from the types here. So one of the other things that I wanted from doing this sort of thing in Idris was when I tried to encode this in Haskell, the error types were horrific, and it just didn't give you a good idea. Like I could barely justify doing it to myself, let alone to anyone else that I liked. So I think this is an amazing improvement on the error types that you get with Haskell. So it clearly states what your preconditions are, what things are in scope, what states are in scope, and what postconditions you have. And there's extra help in the Idris library where you can basically have something like a type hole and go, I don't know what resources I have here. Can you tell me what resources I have here? Or I've dealt with these particular ones, but not these other ones. So there's a lot of help to consume these sorts of errors. But I think that's pretty nice as an error. That's like out of my Emacs buffer. It's pretty good. So how are we going for time? Okay. I just want to point out the related work. So this is very much related to algebraic effects in Idris, Haskell, and PureScript. There's some more expressive power in this ST encoding than there is in algebraic effects. It's also somewhat related to session types and linear types as well. And have a read of State Machine, or State All the Way Down, which is the paper that introduced this concept and introduced the library, although it's moved on a bit from there. So some of the code in that particular paper doesn't work anymore because they've done extra work on various bits. But thanks.